The Andromeda Galaxy played a pivotal role in reshaping our understanding of the universe and our place within it. Our galaxy, for example, is the Milky Way galaxy, and the nearest galaxy to us is the Andromeda Galaxy. We think there are about 100 billion galaxies in the visible universe. It served as compelling evidence that the cosmos and the concept of creation don't revolve around Earth. This discovery shattered the notion that the Milky Way was the sole galaxy in existence, suggesting that we are just a tiny part of the vast universe. While we have accumulated knowledge about Andromeda over the last century, much of it was gathered from observations made on Earth. However, with advanced tools like the James Webb Space Telescope now at our disposal, our perspective has drastically changed. Surprisingly, the recent data obtained from the James Webb Telescope has upended our previous notions about the Andromeda Galaxy. Another cosmic puzzle needs to be solved. The JWST has received signals from our neighboring galaxy, leaving the entire scientific community astonished. Join us as we explore how the JWST received an alarming signal from our neighbor, the Andromeda Galaxy. Indeed, the perception of the Milky Way has undergone significant changes over the course of human history, shaped by our evolving understanding of the cosmos. In the past, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and mythologies. It was often seen as a mystical and central element in the cosmological beliefs of different cultures. As our scientific knowledge advanced, particularly with the development of telescopes and the work of astronomers like Galileo Galilei, we began to realize that the Milky Way was not just a celestial concept but a vast collection of stars, planets, and other celestial objects. This realization revolutionized our understanding of our place in the universe. Today, thanks to modern telescopes and astronomical research, we have a much clearer picture of the Milky Way as a barred spiral galaxy containing billions of stars, including our own Sun. In the 1920s, Edwin Hubble, an American astronomer, made a transformative discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble observed distant nebulae beyond the Milky Way. Through the observations and analysis of these objects, he showed that they weren't actually part of the Milky Way, but were entirely separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. The Andromeda Galaxy has a rich history of observations that dates back centuries. One of the earliest known records of the celestial object can be traced back to the 10th century, when the Persian astronomer Abdul al-Rahman al-Sufi described it as a small cloud in star charts from that period. The significance of these observations lies in the fact that al-Sufi was able to identify this distant cosmic entity without the help of telescopic instruments, relying solely on his keen eyesight and observations. It wasn't until 1612 that a detailed description of the Andromeda Galaxy, based on telescopic observations, was provided by Simon Marius. His work laid the foundation for future astronomers to study this massive cosmic structure. Later, in 1764, the renowned French astronomer Charles Messier catalogued the Andromeda Galaxy as M31 in his well-known Messier catalogue, mistakenly attributing its discovery to Simon Marius. However, that doesn't diminish Messier's role in putting Andromeda on the map. For almost 100 years after these observations, astronomers worldwide sought to understand more about this mysterious galaxy, each adding to the last one's findings. Before that, Galileo Galilei, an Italian astronomer, revolutionized our understanding of the Milky Way in the early 17th century. Using his newly developed telescope, he made groundbreaking observations that challenged the prevailing Aristotelian cosmology. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work An Original Theory or New Hypothesis of the Universe. According to Wright's speculation, the Milky Way was not a random distribution of stars in space, but a completely flat layer of stars. He also suggested that a portion of this vast structure was our own solar system. While Wright's hypothesis was a step forward in understanding the structure of the Milky Way, it was still limited by the observational technology available at that time. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864, when the English astronomer William Huggins made a groundbreaking observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical gaseous nebula. This observation paved the way for the world to understand Andromeda for what it really is. The Andromeda Galaxy has a mass estimated to be between 1 and 2 trillion times that of our Sun, making it a colossal cosmic structure that just happens to live relatively close to us in the vastness of space. In all the research conducted until now, scientists believe that Andromeda is about 10 billion years old, making it quite ancient in cosmic terms. One intriguing aspect of Andromeda's origin is the hypothesis that it came into being through the merging of several smaller protogalaxies. This suggests that over billions of years, smaller galactic entities gradually came together under the force of gravity to form the majestic Andromeda Galaxy we see today. Galactic mergers are common occurrences in the cosmos, shaping the growth and structure of galaxies. However, for a long time, astronomers thought Andromeda was significantly more massive than our own Milky Way galaxy. This misconception is understandable considering the limitations of the observational tools available in the 1700s and 1800s. Recent research has brought about a re-evaluation of these beliefs. New findings have led scientists to somewhat reduce their estimate of Andromeda's mass, while simultaneously increasing the mass attributed to our Milky Way. The current understanding is that the masses of these two cosmic giants are much closer than previously thought. So if you were to be on Andromeda and looked at Earth, you'd see just as massive of a galaxy. This puts into perspective how colossal the Milky Way itself is too. The Andromeda Galaxy's physical dimensions, though, are what astronomers totally agree on. It's known to stretch farther than our own Milky Way, with an impressive diameter of about 220,000 light-years. Andromeda surpasses the Milky Way's estimated diameter of roughly 100,000 to 175,000 light-years, making it a truly significant cosmic entity taking over a large region in space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. In the heart of the Andromeda Galaxy, the supermassive black hole exerts an immensely powerful gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow elliptical paths similar to planets orbiting the Sun in our solar system. At a certain point in their elliptical orbits, stars come closest to the black hole, and this point is called the perihelion. At the perihelion, the gravitational forces are at the strongest they can ever be, causing the stars to move at their highest speeds. This is when the stars bunch up and become more concentrated in space around the black hole. As they bunch up, the stars release energy in the form of radiation, including visible light and other types of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galactic core of Andromeda's AGN, active galactic nucleus. This distinctive feature provides valuable clues about the gravitational dynamics and interactions between the supermassive black hole and the surrounding stars. To understand this better, let's take a look at what an AGN is. The active galactic nucleus, popularly known as AGN, is a highly energetic region at the center of a galaxy. It is characterized by intense emissions across various wavelengths, from radio waves to X-rays. AGNs are powered by the presence of a supermassive black hole at the heart of the galaxy. These supermassive black holes are incredibly dense regions in space, where an enormous amount of mass is concentrated within a very small volume. When astronomers observe the active galactic nucleus using advanced telescopes like the Hubble Space Telescope, they notice a very interesting phenomenon. One of the most fascinating features of the Andromeda Galaxy is its AGN. It appears to have 2 points of concentration, meaning there are 2 distinct regions where light and other forms of radiation are emanating more intensely than in the surrounding areas. The brighter concentration is the second point of focus, which is just slightly off the true galactic center. Within this area lies the supermassive black hole. The mass of this black hole has been estimated to be between 1.1 to 2.3 multiplied by 10 to the power of 8 solar masses, which means it weighs approximately 110 to 230 million times as much as our Sun. Supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and they play a crucial role in the evolution and dynamics of galaxies. When matter such as gas and stars gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various wavelengths, which is why the AGN is highly luminous. When astronomers observe the active galactic nucleus of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature is a result of the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda Galaxy also has another super interesting feature: an abundance of globular clusters. These globular clusters are tight groups of stars that orbit around the center of the galaxy, kind of like satellites revolving around a planet. These clusters play a crucial role in understanding the dynamics and history of the galaxy. One remarkable cluster is Mayol 2, also known as Globular 1, which holds the distinction of being the brightest globular cluster in the local group of galaxies. Mayol 2 is of significant interest because it shares several characteristics with the Omega Centauri globular cluster in the Milky Way. Both clusters are densely packed with stars and have similar masses and sizes, making them excellent subjects for comparative studies. Studying these clusters can provide astronomers with valuable insights into the formation and evolution of galaxies, as well as the properties of the stars within them. Andromeda's rotation is another area that astronomers have meticulously studied. Andromeda is so big that it would take 250 million years for the galaxy to complete just one rotation. This rotational motion reveals the dynamic nature of the galaxy, and it also affects how stars and other objects move within it. The rotational period is an essential parameter for understanding the mass distribution and overall structure of Andromeda. While many of Andromeda's features have been well documented, certain discoveries made with the help of the James Webb Space Telescope have raised eyebrows among astronomers. The JWST has an uncanny ability to study the universe using infrared light. This means it can peer through dust and gas that typically obscures our view and see the birth of stars, galaxies, and other cosmic phenomena. One of the most astonishing aspects of the JWST is its capacity to detect infrared light from objects that are billions of light-years away. This extraordinary capability allows astronomers to observe some of the earliest galaxies that formed after the Big Bang, which occurred around 13.8 billion years ago. By studying these ancient galaxies, scientists can gain insights into the processes that shaped the universe in its infancy. Additionally, the JWST's high-resolution imaging capabilities provide unprecedented views of the structure and composition of distant galaxies, stars, and planetary systems. One of the most groundbreaking discoveries made by the JWST is its ability to detect biosignatures in the atmospheres of exoplanets. Biosignatures are chemical compounds or other indicators that suggest the presence of life. By analyzing the light passing through the atmospheres of distant exoplanets, the JWST can identify the presence of gases such as oxygen, methane, and water vapor, which are essential for life as we know it. This opens up new possibilities in the search for extraterrestrial life and the exploration of potentially habitable worlds beyond our solar system. Furthermore, the JWST has been instrumental in unraveling the mysteries of black holes and their interactions with surrounding matter. Its observations have provided detailed information about the accretion disks and jets associated with supermassive black holes, shedding light on the complex physics governing these extreme cosmic objects. The Andromeda Galaxy has particularly benefited from the JWST's capabilities. One surprising discovery was that the JWST received signals from Andromeda. However, the implications and interpretations of these signals have left scientists with more questions than answers. These unexpected signals from Andromeda have sparked intense debates and further investigations within the scientific community. Some scientists speculate that these signals could be related to previously unknown cosmic phenomena or interactions within the galaxy. Others suggest that they might be the result of complex processes occurring in Andromeda's core or within its active galactic nucleus. The signals have prompted astronomers to delve deeper into the intricacies of Andromeda, utilizing the advanced capabilities of the JWST to gather more data and unravel the mysteries of our neighboring galaxy. Additionally, the JWST's ability to study the Andromeda Galaxy in unprecedented detail has revealed new insights into its star formation processes, the distribution of dark matter, and the dynamics of its various stellar populations. These findings are not only enhancing our understanding of Andromeda, but also providing valuable comparative data for studying other galaxies in the universe. As the JWST continues to observe and analyze Andromeda and other celestial objects, astronomers anticipate that it will uncover more hidden secrets and offer fresh perspectives on the evolution and nature of galaxies. The James Webb Space Telescope's remarkable capabilities are expanding our knowledge of the cosmos and pushing the boundaries of our understanding, making it an indispensable tool in the ongoing exploration of the universe.